Okay, so I was still saying, I don't know how my mic got muted. I was still saying, Semakula and area, you help me coordinate the people raising up their hands or any feedback in the chat. So on that note, can someone lead us in a word of prayer?
Let's pray. Gracious Father in heaven, thank you for the life you've given us. Lord, as you're going to study, send your Holy Spirit to give us wisdom. Because when you are not there, we can't understand these things. Be with us in thy name I pray. Amen.
Amen. Thank you for that prayer. So we are going to begin from where we stopped. Who can remind us where we stopped last week? Or who can give us a wrap up on what we looked at last week?
Technopop 5, please unmute.
We learned about carbon in life.
Yeah.
Okay, thank you. Anyone else?
Bella has hand raised.
We stopped on the physical properties of alkynes.
Okay, thank you. So the pronunciation of that word is alkanes, because when we get to alkynes, it will also be there.
Thank you.
Okay, thank you too. Okay, so just a brief on what we studied last week. We started on a topic called carbon in life, and we said carbon in life basically deals with us knowing that different substances we interact with have carbon in them. And then we also looked at what a homologous series is, and we said it is basically like a family that has a same general formula and similar chemical properties. So we looked at alkanes and we found out the general formula of alkanes. Who can remind us the general formula we found out for alkanes? Anyone that remembers?
Narrowness. Okay, Jeremy, unmute.
Cn H2n+2.
Okay, that's very good. Thank you. So we said they have a general formula of Cn HN H2n plus 2. And we said alkanes is one of the homologous series. And like we saw, they have the same general formula. So whether you want to find how many carbon atoms are in ethane, how many hydrogen atoms are there, you'll use that formula. If you want to find out how many are in octane, still you'll use that general formula. And we also noticed that alkanes end with ANE, which are the last three letters on the name alkane. So we had stopped on the chemical properties, sorry, the physical properties of alkanes, and we had started looking at a few of them. So I had tasked us to get a model for any alkane that you could possibly want to form a model for. I don't know how many of us went ahead and did that. And then also, I want to appreciate those people that were able to send in their work to be marked. And for those where I asked you to make corrections, I hope you were able to do that. So the physical properties, we had mentioned boiling and melting point, and we had seen this graph. And someone had commented that the graph is not so clear, but I had told us that the orange was representing the boiling point, while the blue was representing the melting point. And I said on the horizontal axis, we have the number of carbon atoms running from 1 to 16. And then on the vertical axis, which you call the y-axis, we had boiling point and melting point scale. So that means at that point, someone had told us in a previous lesson that there is a general increase in both the boiling and melting point. And I had gone further to explain that and said that the general increase is brought about the more the number of carbon atoms increases. That means even the bonds holding those molecules are more. So if we have, for example, one carbon atom like we can see here, you realize that at this point, where you have one carbon atom and where you have 16 carbon atoms, you notice that the boiling point and melting points are higher than when you have one carbon atom. So that means the number of carbon atoms has increased. And because the number of carbon atoms has increased, that increases the molecular mass. So for example, maybe we had one disk. If we add more disks, that means the weight of those disks is going to increase. That means the mass will definitely have to increase. So it's the same thing here. When we have one carbon atom, the mass is lower compared to when we have 16 carbons. Because remember, each carbon is going to be bonded to hydrogen atoms and also to other carbon atoms. So definitely the mass increases. And if the mass is increasing, that means the van der Waals forces of attraction also increase in that given molecule. So that is what causes the melting and boiling points to be higher. So here we have the explanation and other properties. So we have why do melting and boiling points of alkanes vary with the number of carbon atoms? So we said melting and boiling point increase with increase in molar mass, and I've explained this. The more the number of carbon atoms increases, that means the more the elements are, and that means their mass increases. And of course, you're going to discover more on molecular mass when you get to the next topic in senior 3 that you'll be learning. And then of course, I've said since the molecular mass increases, therefore the van der Waals forces of attraction also increase. Van der Waals forces are those forces that are holding those bonds together. So those bonds contain those forces and they're the ones that keep them together. And then we have identify and explain other physical properties of alkanes. Like we already say, you don't just get to the lab and say every colorless solution there is water. So that means alkanes, more like water, they are colorless and they are odorless. They have no smell. And then, of course, you're going to notice the physical states. When I asked last time, people told me we can look at their physical state, we can look at their solubility, we can look at their density, we can look at boiling and melting points, we can look at color. So these are some of the physical properties well explained in terms of those different properties you gave me in the last lesson. So you realize that alkanes from 1 to 4 are gases. Can someone remind us the names of those alkanes? The ones that have one carbon atom, 2 carbon atoms, 3 carbon atoms, and 4 carbon atoms. Who can remind us the names of those compounds?
Meth, eth, prop, and bat.
Okay, can you correct that? Because those are just prefixes, but give us the full name of those alkanes.
Technopop.
Madam, can I give it?
Yes, please.
For 1 carbon atom, we have methane. For 2 carbon atoms, it's ethane. For 3 carbon atoms, it's propane, and then 4 carbon atoms, it's butane.
Butane. Okay, thank you so much. So, that means methane, ethane, propane, and butane are gases. So when we are looking at those alkanes, we term them as gaseous instead. And then when we go to those that have 5 carbon atoms to 17 carbon atoms, those ones are liquids. And then from 18 to more until infinity, basically, those ones are what? Are solids. So it's important that you know the different states in which those alkanes exist. From 1 to 4, we've said they are gases. From 5 to 17, they are liquids, and those that contain 18 carbon atoms and more are solids. And then, of course, we also have to understand that alkanes are insoluble in water and soluble in organic solvents such as benzene. Remember, these organic solvents can dissolve in fellow organic solvents. So that means alkanes do not dissolve in water because water is an inorganic solvent. Yet they dissolve in organic solvents such as benzene. And I don't really want to go into the details of benzene. For those of us who do chemistry at A level, you will get more explanation on what benzene is. And then we also look at the density. And of course, density increases with increase in molecular mass, but branching reduces this trend. So when we look at the density increases with the increase in molecular mass. And I've already explained that the longer the chain, that means the higher its molecular mass is. So that means a carbon atom with one carbon, a given compound with one carbon atom and another compound with 3 carbon atoms. The molecular mass of the one with 3 carbon atoms is higher than that one with 1 carbon atom. So basically, density increases with the increase in the molecular mass and branches this trend. So some chains, when they are very long, they tend to branch off and make branches, like how you could see a tree having different branches. So it's the same thing. When the molecular formula of this given compound is so long, it's going to end up having those branches within it. So, for example, I was saying this, you realize that this one is a longer chain, so it can choose to branch, whereby this carbon can tend to, you can tend to have it come here. Instead of it continuing to be a longer chain, it will start to form those what? Those branchings. So this one here will have a higher density compared to this one that what? That branches. So basically, I think that's it. Are we all together on those physical properties of alkanes?
Yes.
Okay, thank you for that feedback. Okay, thank you. So these are the different formulae and different melting points and boiling points of the different alkanes. And when it comes to melting and boiling point, like we always know that, for example, -183 and then -182.8, we realize that this is higher than this one here because of the negative values. The hosts, can you please help me mute those people whose mics are open because it's sending irritating feedback. Please mute them. Thank you. So, I was saying, when you look at the melting and boiling points, you notice that there is a general increase in the melting point values and there is a general increase in the boiling point values. Okay, so I think I sent that slide as well on the group for those that are on that group. Then when it comes to alkanes, we also have chemical properties of alkanes. So among the chemical properties, we look at how alkanes react with other substances. So some of those properties we are going to look at, one of them is combustion. And we know that combustion is burning a given substance in oxygen. So alkanes basically undergo two reactions. And those two reactions, we have combustion and halogenation. Halogenation is the addition of halogens to a given substance to form a compound. So among the halogens, we have fluorine, we have chlorine. All group 7 elements are called halogens. So I believe when looking at the periodic table, your teachers must have mentioned that group 7 elements can also be called halogens. So we have fluorine, chlorine, we have bromine, we have iodine. But I am certain that you looked at only fluorine and chlorine because they are the elements that are under the first 20 elements of the periodic table. These ones are beyond the 20 elements, but it's good to know that there are also group 7 elements referred to as halogens. So when we are looking at halogenation, it's basically the addition of that halogen to a given element in order to form a compound. And then when we look at combustion, combustion I've said is the burning of a substance in air or in oxygen. So with that, we have an experiment of combustion of an alkane. And the basic alkane we can use, at least I know most of us know what a candle is. At least you've heard about it, at least you've seen it, maybe in church, maybe at home. Somewhere at least you should have seen a candle. So there is this diagram. It may not be so clear, but I want you to listen in as I explain so that you know what the different containers have. So this first container, the first setup here, where I have put this red marking, is a stand on which a candle has been placed. So a candle is one of the greatest example of an alkane. So this candle, we are yet to find out what it contains. So this is a candle. Then, of course, a delivery tube, taking on the vapor from the candle into this beaker. This beaker is containing anhydrous copper 2 sulfate, anhydrous copper 2 sulfate, and then this last beaker is containing calcium hydroxide, or what we call lime water. Or it can be called lime water. So this experiment is helping us find out if we burn an alkane in oxygen, what is going to happen. So like I have said, a candle is an example of an alkane because it's a hydrocarbon. So a candle is also basically contains what we call methane. So methane, when burnt in oxygen, is going to give us two products. And those two products are the ones we are testing for in the first beaker and then in the second beaker. Of course, we have the cold water, or in most cases, they call it ice water. So remember, when this vapor comes in from the burning candle, it's going to move into the beaker with anhydrous copper 2 sulfate. And if you looked at water in senior 1, your teacher must have told you that anhydrous copper 2 sulfate is used to test for the presence of what? Of water. So when the vapor moves into this beaker, this cold ice is going to cause that vapor to what? To cool. That's why that beaker is placed in a water bath. So it's going to cause the water to what? To cool. When the water vapor cools, definitely the colorless anhydrous copper 2 sulfate is going to turn to blue to prove that that candle vapor contained what? Water in it. And then, of course, the gas, which is carbon dioxide, is going to continue. That's why we have another delivery tube here, this delivery tube. So it is transferring the vapor of carbon dioxide into the next beaker, which has lime water or calcium hydroxide. So once it reaches there, you're going to find that this colorless solution of calcium hydroxide now turns to a white precipitate. And that will prove that carbon dioxide is actually present in a burning candle. So when we burn a candle which contains methane in oxygen, it's going to give us carbon dioxide gas plus water as its products. And that is enough to prove to us that a candle is a hydrocarbon, because when it burns in oxygen, it provides carbon dioxide and water as its products. People, are we together?
Yes, madam.
Okay, thank you. So I have some few questions in line with what we've just learned up there. Identify two major elements that make up a hydrocarbon. Who can tell us those two major elements that make up a hydrocarbon?
Let's hear from Noeline Maria. Please unmute.
Thank you. Good afternoon, madam.
Good afternoon.
The two major elements which make up hydrocarbons are hydrogen and carbon.
Okay, very good. Thank you. So we said they are carbon and hydrogen. That's very good. So what happened to the anhydrous copper 2 sulfate solution and why? I've just explained that. Anyone to tell us what happened to the anhydrous copper 2 sulfate solution, and you tell us why.
Let's hear from Emanuela. Okay, she has gone off. Let's hear from Phoebe.
Um, the anhydrous copper 2 sulfate turned blue due to the presence of water in the vapor that came out of the burning candle.
Okay, thank you. That is very good. Sorry,
Okay.
so we said, okay, do we have someone else?
Yes, we have Frida,
Okay.
please. Unmute.
I think anhydrous copper 2 sulfate turns blue to indicate us that a burning candle contains water.
Okay, thank you. That is very good. Do we have anyone else
No,
that has a
please.
different? Okay, thank you. So we've said the anhydrous copper 2 sulfate turns, in chemistry, you have to learn to give the original color and then the color it turns to. Turned, since they said what happened, so it's turned from colorless to a blue solution. And of course, we say because of the presence of the water vapor that comes from the burning candle. So that's very important for you to take note of. So we continue and say, what other substance can be used apart from anhydrous copper 2 sulfate, and state the expected observation. So I am sure your teacher mentioned another substance that we could use to tell the presence of water in a given substance. What substance was that apart from anhydrous copper 2 sulfate?
We have no hands raised.
And in the chat?
There are no responses too.
Okay, so have we heard about the cobalt
But
2 chloride
yeah,
paper? Sorry?
Happy's hand just came up. Happy, please
Okay, she can
unmute.
go ahead.
Madam, I was
Yes,
asking,
please.
I don't know if this is silly, but can lime also be used to detect if water was there?
Can what? Anyone who had her question?
Happy, please
I
unmute
don't know.
again and
I was asking that can lime also be used to detect if water was present?
I'm not getting the last words I'm hearing. Can lime be used to investigate? I don't know what you're saying last.
let us hear from Angel Unique. Angel Unique, please unmute.
Madam, she's saying that can lime be used to detect if water was there?
What does she mean by lime? Because I think we already mentioned that lime water is used to test for carbon dioxide, and that lime water can also be called calcium hydroxide solution. So I don't know what lime she's referring to.
Okay, hope Happy you've got it. Let's hear from Maria Simwe. Please unmute.
Another substance that can be used apart from anhydrous copper 2 sulfate can be cobalt chloride, which is sky blue generally, but on exposure to water or water vapor, it absorbs it and changes to purple and then pink.
Okay, thank you. That is very good. So the other substance that can be used to test for the presence of water can be cobalt 2 chloride solution, which is blue, or we can use cobalt 2 chloride paper. So cobalt 2 chloride turns from blue to pink in the presence of water. So we said for anhydrous copper 2 sulfate, it turns from colorless to blue, while for cobalt 2 chloride, it's blue, but it turns to pink in the presence of water. So I hope that is clear for all of us. So then we have our next question here, which is saying, what happened to the calcium hydroxide solution, and give a reason for your answer.
Phoebe, unmute.
The calcium hydroxide solution turned into a white precipitate because it turned into a white precipitate, indicating that the vapor from the burning candle contained carbon dioxide.
Okay, that's very good. Thank you. But like I said, always state what color it was before and the final color, because it helps identify the change that occurred. So, of course, we said colorless calcium hydroxide solution turns to a white precipitate due to the presence of carbon dioxide. Okay, so that's great that people are actually paying attention. Then write for the reaction, the equation for the reaction that takes place. So here we have calcium hydroxide plus carbon dioxide giving us calcium carbonate plus water. Always endeavor for your equation to be on one line. Mine shifted because of the space of the phone, but always endeavor that your equations are on one straight line and the arrow must be there to differentiate the reactants from the products. And like I said, when we are burning a candle, you need to have that word equation somewhere. So if you're seated with your notebook, which you should, plus oxygen, so you can write the word equation, giving us carbon dioxide gas plus water. Such that it can let you know that when you burn a candle in oxygen, it will give you carbon dioxide gas and water. So I hope that is clear. So what is the use of the ice cold water?
Enosh, please unmute.
It's to cool the vapor that comes from the candle.
Okay, that's very good. Thank you. So we say the ice cold water is to cool the vapor that comes from the burning candle. Okay, so there is a conclusion here that a candle and methane belong to the same homologous series, and therefore the equation I've already written that one. I don't think I need to rewrite it. Rewrite methane plus oxygen giving us carbon dioxide and water. So that is the equation for the reaction when methane burns in air. So that is one way of proving that when alkanes are burnt in air, when alkanes burn in air, they will definitely give us carbon dioxide and water. So that is one of the evidences that we can base on, that when we burn a hydrocarbon in oxygen, it's going to give us carbon dioxide plus water. So for halogenation, we will not look at it at this level. But like I said, most of you that will do chemistry, at A level, you will look at most of these things and even in deeper context. So one of the alkanes we have in our daily life is called crude oil. This crude oil is also called petroleum. And in this lesson, you're going to discover that petroleum and petrol are not the same. They are two different terms. Petrol is a fraction of petroleum. So when you say petrol, you're speaking about something that was obtained from petroleum. When you speak about petroleum, petroleum is a composition of very many things, as we are going to see in this lesson. So when you're talking about crude oil or petroleum, you're talking about the same thing. So I have a few questions for us here. that I want us to answer together. What is the color of crude oil?
No, Ernest.
I think crude oil is black.
Very good. Crude oil is black. Any other color that we know crude oil can be?
Okay, maybe let's hear from Maria Sima.
Light yellow.
Wow, light yellow. Okay, can we improve that one? Because if we compare black, then light yellow, do you think there is a comparison there? So let's get a
It
color.
darkens.
Sorry?
It darkens. Oh, it is usually light yellow. It darkens, like it becomes black when it's exposed to light. But often fresh crude oil has a yellow to green blue fluorescent.
Okay. Though when we are
Yes.
looking at crude oil is more of a darker thing, so it's not light yellow. I know you may have read it from Google or somewhere, but crude oil in its appearance is not usually light because it's a heavy thing. Okay. Do you have any other suggestions?
Yes. Kaylee
Mm-hmm.
tells us it's black. Jeremy tells us it's brown. Sam Junior says it's black, and then Ajoya Marvin says it's brown.
Okay, thank you for that feedback. That's so good. So crude oil is a thick, dark brown or black liquid. So it is either thick, dark brown or black. So you can give either of those two colors. Thick, dark brown or black. Don't give both, choose one, because usually when we tell students an alternative, they usually state both of them. So always choose your best alternative. Okay, so what is the other name of crude oil?
Okay, Jeremy, you can give us your feedback.
Petroleum.
Petroleum, very good, thank you.
Okay.
Next question. Why is crude oil known as a fossil fuel?
Maria Simwe.
Crude oil is referred to as a fossil fuel as it is naturally formed from the Earth's crust and is a carbon compound or hydrocarbon.
Okay, thank you for that suggestion. It's found in the Earth's crust and it's a hydrocarbon. Okay, thank you. That is good. Any other?
Yes, let's hear from Rina.
I think crude oil is known as a fossil fuel because it's mined from underground where like fossils come from.
Okay.
Okay,
Then
thank you.
we also have Marceline Glenn. She's telling us that it is got from fossils or dead plants and animals. That's for feedback from the chat.
Okay, thank you. So, fossil fuels, we know they are obtained from dead organic matter or dead living things. So basically, crude oil is known as a fossil fuel because of that. It's obtained as a result of decomposition or decay of living organisms over millions of years. So that is why it's called a fossil fuel, because it's decomposing living organisms over a given period of time. And most of the fossil fuels, for those of us interested in archaeology, you're going to notice that there's a result of decay over a given period of time. So it states it was formed from remains of living organisms that lived many million years ago. So when they ask how crude oil is formed, you need to include the fact that it's obtained, first of all, from remains of living things that lived many millions of years ago or over very many years ago. It is very important for you to be particular about the time that decay takes place. And then, by what process is crude oil formed? Who can tell us?
Okay. Doreen, please unmute.
It is formed through composition.
I don't think I got that. Isaac, were you able to pick what she said?
Yes, she said that it's formed through decomposition.
Okay, that's very good. Any other suggestions?
Yes. Maria Martha, please unmute.
Personally, I wanted to add on something to our question before. I think we should include that crude oil, being a fossil fuel, is also burnt to produce energy.
Okay, thank you for that suggestion.
Because fuels are mainly burnt to produce energy. So
Okay, thank you. Though that will come in at a later stage, because at this point we are looking at why is it known as a fossil fuel? Why do we call it a fossil fuel? So we are not basically looking at how it's obtained, or how should I phrase that? I hope it's able to communicate, but that's very true because it's burnt, as we are going to see in our next stages. And of course, its burning gives us the different fractions that we are going to see. Okay, any other hands up?
Let's hear from Joshua Daniel. But before, in the chat, all the feedbacks are saying through, it's formed through decomposition. Yeah.
Ale, thank you. That's good. So, Joshua, you were saying something?
Yes. I was saying I have something. According to my research, crude oil is formed through a process called diagenesis and catagenesis.
Okay, do you mind telling us what those mean?
Joshua?
Uh, uh, Diagenesis, this is the first stage of transformation, involves the breakdown of organic matter into simpler compounds as it is subjected to pressure and mild heat, turning into a substance called kerogen. And catagenesis, as the kerogen is buried deeper and subjected to even higher temperatures and pressures, it undergoes chemical reactions, breaking down into hydrocarbons such as oil and natural gas. This process typically occurs at depths between 2,000 and 4,000 meters. Thank you.
Okay. Thank you, Joshua. So, according to Joshua's explanation, you can notice that diagenesis is basically about the decomposition of that organic matter. And then when we go to the catagenesis, you're looking at the fractional distillation of how that crude oil is being broken into the different fractions that we use later on. Thank you, Joshua. That is good. So, the process of crude oil being formed is basically by decay and decomposition of living organisms over millions of years. So you're going to understand that since it's picked from underground, it's subjected under pressure, which causes these living organisms to decompose over a million of years, and they're able to form that crude oil. I hope that is clear for all of us. So our next question is, how is crude oil purified? Because remember, we've looked at how it is obtained. So how is it purified?
And Joshua Daniel.
Crude oil is purified by refining it, probably.
Okay. By what? Could you say that again?
Joshua. I think I was trying to say that it's purified through refining it.
By refining it.
Okay. Thank you. Do we have any other hands up?
Yes. Maria Martha.
Crude oil is purified by the process of fractional distillation.
Okay, good. So since we talked about the different fractions that we need to obtain from crude oil, that means the way we purify it is by fractional distillation. And we said fractional distillation, we use it for those substances that have differences in their boiling point. Don't just say it's purified by distillation. It must be fractional distillation. So what are some of the fractions we expect to get from crude oil when we fractionally distill it? What are some of the fractions we expect to get from crude oil when we fractionally distill it?
Jeremy.
We have petrol, paraffin, kerosene, and others.
Okay, thank you.
Okay, thank you.
Anyone else?
Anyone?
With
Okay.
any other fractions?
Lubega Vincent, unmute.
There is oil and diesel.
Okay, good. Any other?
Please unmute. Okay, let's hear from Akulo Philomena.
Yes, I have residuals. The residuals.
Residuals, okay. What are those residuals called?
Okay, she's not responding. Kaylee, please unmute.
What about coal?
Coal, not really. But thank you. So we look at the different fractions. We have natural gas or gas. We have petrol, we have kerosene or paraffin. Please choose one of those words. Don't use both of them because they are the same thing. Then we have diesel. We have lubricating oil, which someone called oil. We have wax. And then we have bitumen. I don't know how many of us have heard of that one. We have bitumen. So those are the different fractions we are going to obtain while using fractional distillation. And we know that fractional distillation has different trays or cooling trays. I know you looked at that when you were looking at the purification of air, or how we obtain oxygen, liquid oxygen. So the same procedure is more like the same. So you realize that the trays above are cooler than those that are below because the furnace is closer to the trays that are below. I have a diagram here, though it may not be very clear on your screen, but I just want you to follow through as I explain, because I failed to get a better resolution for the diagrams I used. So sometimes you may need to pay more attention while I explain. So we've answered these. We've said, describe how crude oil is separated into its pure components. Of course, that is the fractional distillation process. And then the method used is fractional distillation, the different fractions, we've mentioned them. And then, of course, the uses you're going to tell me after we've explained using this diagram. So the diagram here is showing the crude oil, then the furnace. Like I've said, the trays closer to the furnace are hotter than the trays that are up. So this tray is cooler than this one here because it's far from the furnace. And that explains why those of lower boiling point are the ones that go higher, because they can easily vaporize. So if they're in vapor form, they will move to the upper trays. But you realize that as you go down the trays, since they are hotter, and that means the heavy components settle on those trays that are what? Are below. So the first one given off is natural gas. And then we also have the next one being cooled off is petrol. Then the next one cooled off is naphtha. Then the next one is paraffin or kerosene. Like I said, choose one word that you could use. You can say paraffin, or someone else can say kerosene. And then the next one is diesel. The next one is fuel oil. The next one is lubricating oil. Lubricating oil. Then the last one is bitumen. And in some diagrams, you'll find after the lubricating oil, they'll put wax, or some others, they'll combine both wax and bitumen together. They will just say wax and bitumen. So we all know wax is a bit heavy and bitumen the same thing. So that is why you find that they are the bottom trays, because they are in solid state. Okay, molten state. It may not be solid, but it's that heavy liquid. So basically, those are the fractions that we obtain during the fractional distillation of crude oil. And of course, you could give an example of petroleum is pumped through a furnace. For example, here, crude oil is pumped through a furnace of about 400 degrees Celsius. And then, of course, the crude oil is passed into the fractionating tower, which consists of trays at different levels and different temperatures. So, of course, the hot mixture of gases and vapors will be passed to the top of the tower, and each of these fractions cools off at a tray of its temperature. And then, of course, they are collected off according to their different boiling points. And then also you need to understand that The commonest impurity during this procedure is sulfur. And this sulfur is used in the manufacture of sulfuric acid. So when it's collected off, it's not just disposed of anyhow. It can be taken for the manufacture of sulfuric acid. So after explaining that, you talk about the uses of those different fractions, and we are going to start with natural gas. Can someone tell us what is the use of natural gas?
Zara, please unmute.
Good afternoon, teacher.
Good afternoon to you.
Natural gas can be used for cooking.
Very good. Thank you, Zara. Anyone else?
Treatney, please unmute. Okay, in the chat, in the chat, Jeremy says it's used in cooking. Okay, Joshua Daniel, unmute.
Natural gas can be used in industries like for manufacturing products.
Products like which ones? Because when you talk about manufactured products, you must convince us which products is it used to manufacture.
Like
Okay, okay.
Fertilizers and petrochemicals, stuff like that.
Okay, thank you. So, some of the basic uses we look at when we are looking at natural gas, we look at the fact that it can be used in cooking. Most of these days, people are using gas cookers. So those gas cookers contain methane, butane, propane, depending on the composition. So you find that natural gas is used in cooking, and it's also used in lighting. So some people use that gas if it's sufficient enough and you know the watts of your bulb, you can connect and then your house will be lit up. And then what is the use of petrol?
Nama Weje, please unmute.
Madam, petrol is used for running car engines, and I'm requesting if you would at least give pardon on the description of fractional distillation. How can I describe it in case I'm given a question about it?
Okay, I'll re-explain that, but after getting the different uses of the fractions. And if we are not able to, you'll go back and watch the video because that explanation will be there. So I'll do that, but after the different uses of these fractions. Okay, anyone else? Thank you for that submission of used as a fuel.
Maria Martha.
Petrol is used in the petrochemical industry, where petroleum is used as a raw material to make products like plastics and polythene.
Okay, then from the chat, Yasmin says that Natural gas can be used. Sorry, this was for the first one. But it was saying natural gas can be used for welding. Yeah.
Okay, so we said petrol can be used in motor or aviation fuel, and at least these diagrams on the extreme end of these different fractions can guide on what your expectation should be. So they can be used, petrol can be used as a motor and aviation fuel. Okay, and then we move to naphtha. Anyone who knows the use of naphtha?
No, Maria Martha.
It is used in laundry soaps and cleaning fuels, and it's also sometimes used for varnishing, and also it's used as a fuel for clamp stoves, and also it's used for paint.
Okay, great. Yeah. In the chat, Oppo says naphtha can be used as a solvent for industrial extraction processes. Yeah.
Okay, thank you. So naphtha has all those different uses. It can be used in varnish, it can be used as a solvent in chemical industries. Okay, so we move on to paraffin or kerosene.
Phoebe.
Paraffin is used as a fuel for heating systems.
Okay.
Then we have onion feeder piece.
I think paraffin is used as a fuel in jet engines in aeroplanes. And also it's used as a fuel in lamps and stoves.
Yes. We have Tritney. Please unmute. Tritney. Oh.
According to me, paraffin is used for heating and lighting in lamps, yeah, and stuff.
Okay. Let's hear also from Rina.
Paraffin could be used in these paraffin lamps to light people, to provide light.
Okay, Joshua Daniel.
Paraffin is used as a coating for tablets and pills to make them easier to swallow or to control the release of the drug.
And Shamatha, in the chat, somebody who was Rina, in fact, was asking if naphtha is similar to naphthalene. And then also Philip asked what is naphtha.
Okay, so naphtha is different from the naphthalene balls. And then, of course, you have to understand that naphtha is a fraction of what? Of petroleum. I think that's the best way I can explain it. If you want more results, you can literally go to the internet, search the images, and have a look at what naphtha looks like, if they can give it to you. But in most cases, those images you're going to find are going to be showing you the different products that naphtha is used to make. For example, soap, for example, the different solvents in which it is found that are used for maybe shoe polish, varnish, and all those different substances. And then you said the first question was what?
She asked, sorry,
Oh,
Philip asked,
naphthalene balls.
yes?
Was it about the naphthalene balls being the same as naphtha?
Yeah. The first question was, what is naphtha? Then the second was, is naphtha similar to naphthalene? Yeah.
Okay, so I think I've answered both questions.
Yeah.
Okay, yeah, so paraffin, those are the different uses that each one of us has given, really. There is nothing for me to add. Then diesel.
Happy, unmute.
Madam, I was saying, diesel is used in diesel engines to generate electricity.
Okay, that's good.
Kaylee, please unmute.
Diesel is used to run engines of vehicles, especially big vehicles. Especially big vehicles.
Okay. Now let's hear from also Frida Peace. Anyone?
Yeah, for me, I think diesel is used in the making of candle wax.
Okay. Those are the... Okay, Joshua Daniel.
Diesel is used in what? In diesel generators to produce electricity.
Okay, thank you all for your submissions. And of course, I still can't add on to those because basically diesel is used in diesel engines. So anything that has a diesel engine can really be used either for production of energy or lighting. Okay, we move on to fuel oil, or what we call gas oil. What is its use?
Happy still. Unmute.
Fuel oil is used in boiling. Okay, it's used in heating things at home or anywhere, and also in power plants to produce energy or electricity.
Okay. Maria Martha.
Gas oil is used in powering machinery, for example, emergency generators.
Okay, thank you.
Tritony. Tritony. Okay. Let's hear from Joshua Daniel.
A fuel is used as an energy resource in the oil refineries.
Okay, thank you. So,
Kimberly Kendall. Kimberly. Okay, those were the responses, teacher.
okay, thank you. So, thank you for the responses. You notice that fuel oil or gas oil, all those uses come in, but its major purpose is really to make petrol, as we are going to see in our next slide. Then, lubricating oil, uses of lubricating oil.
Doreen.
It is used also to reduce friction.
Okay.
Jeremy.
It is used to prevent rusting.
Okay.
Kaylee.
So, just a minute. As you talk about to stop rusting, you need to specify where it is preventing the rusting. So it's important that you talk about where is it preventing the rusting, because if you just say to prevent rusting of what, so please make sure that your answer is well put together.
It is used to prevent rusting in moving parts.
That's better.
Okay. Then Kaylee.
Used in vehicle batteries.
Okay. Then Happy, lastly.
It is used to cool engines in factories.
Yes. Then in the chat, Cheyune Patrin says lubricating oil is used as a hydraulic fluid in heavy equipment, and Musimenta Sandra Flo says for refusing friction. Yeah.
Okay, so those are good answers, and I don't think I have anything to add. So, when we look at wax and bitumen lastly, what are the uses of those two, wax and bitumen?
Okay. Dear Enosh, please unmute.
It's for road and roof surfacing.
Okay, that's good.
Okay. Happy. Go on.
Wax can be used in polishing and also releasing mold.
Then Maria Simwe.
Bitumen is used for waterproofing. That's why it's used on roads and for roofing. And it's also used in making ink. Its powder is used in making ink, paint, cement.
Yes. In the chat, Zara says can be. Sorry.
Isaac, I can't hear you.
Zara was saying it can be used in candles for light. Wax. Then Jeremy says wax can be used for making candles. Cheyune Patrin says it's used as adhesive. Sorry. Doreen says it's used in water repellency. Then Joshua Daniel says it can be extracted and refined to produce usable forms of petroleum products. And then finally, Phillips and Musimenta says for making candles. Yeah.
Okay, thank you for your contributions and thank you, Isaac. So you realize that those are the different uses of wax and then bitumen. So someone asked me to repeat the procedure of how to explain this fractional distillation, and that's what I'm going to do, though I'm going to go through it very fast. So I said, first of all, petroleum or crude oil is pumped into a furnace of about 400 degrees Celsius. So when it's pumped into this furnace of 400 degrees Celsius, the components with lower boiling points are going to rise up because they are lighter and they're in vapor form. So basically, they are going to go to the trays that are cooler and according to their temperatures. So that means the ones that are in the upper trays have lower temperatures, and that's why they cool off at those trays. And then the ones next to the furnace have a higher temperature and they are heavy. That means they will settle at the trays that are in lower positions because of their heaviness and they can't move to the upper floors. So you're going to find that these different these different components are going to cool off according to their boiling points, according to the difference in their boiling points. So when they cool off according to those difference in boiling points, they'll be collected off at those different intervals. And like we said, natural gas has the lowest boiling point, and that's why it's collected off first. And then unlike bitumen and wax, which are heavy, and have a higher boiling point. So you can see its boiling point is above 350 degrees Celsius. So that means at that point, it has a higher boiling point. Therefore, it will be collected off last. So basically, your explanation is to have the crude oil being pumped into the furnace of about 400 degrees Celsius. And then, of course, the crude oil is fed into the fractionating column according to the difference in the boiling points of its fractions. And then of course we'll have the lower one, the one with a lower temperature, with a lower boiling point, which is natural gas being cooled off at the top tray, compared to bitumen and wax, which are of a higher boiling point. And then of course I mentioned that during this fractional distillation, there is an impurity, and the commonest impurity there is sulfur. And that sulfur is collected and used to make sulfuric acid in industries. So I hope I have helped the person who asked me to repeat that. And if I seemed a bit fast, please go back and rewatch so that you can be able to obtain the content as you note down, because my speaking may not enable you to write down, but as you watch again on YouTube, you notice that you'll pause, write that statement, pause again like that. And then I'll also encourage us to research, find a textbook. Don't only rely on Google. Google is good because it quickly gives you the answer, but then that answer may have question marks on it. So if you have a textbook, it's always important that you refer back to those textbooks. You can get Atkinson, you can get Understanding Chemistry, you can get Complete O-Level Science, Chemistry, you can get different textbooks at least to build your learning. And like I said, don't go in the textbook of the old curriculum and you start looking for carbon in life. Look for organic chemistry. That topic is there. Even when you look at the index, it will show you the page it's on. Then you go over those pages. It will help you understand better. And then I'll encourage us during the lesson always take down notes such that when you go back, you review them, such that even when you're reading a textbook or the internet, you're guided. Because remember, there are particular websites as a student you should use, because some of them are going to give you more information which is not necessary at your level, or they are going to give you information that is incorrect. Because like I always say, Google, I can also go as teacher math, I get my answer, I put it there. Whether true or false, it's there. So of course, sometimes we get the correct ones and scrutinize them and ensure that they are at the level we want them to be. So even as you use Google, always be conversant to use a textbook as well. So this slide is just showing the different uses. So I'll go over them very fast, but of course you've given several. So for people who are noting down, you realize that you have several uses, which is good for your revision. So we have natural gas, which is majorly propane and butane, used as a fuel for cooking and lighting. And then we also have petrol, which is used in motor and aviation fuel. Then we have paraffin or kerosene, which is used in lighting and heating, and it's a major fuel in jet engines. Then we have gas oil, which is used to make petrol. We have diesel for diesel engines of trains, lorries, tractors, and someone told us those very huge vehicles. And then also lubricating oil, which is used in lubrication in machine parts or to reduce friction in moving parts of machines. And then, of course, we also looked at waxes and bitumen, which are used in the production of Vaseline, greases, candles, also tar, which is used in road construction and runway surfaces. That black tar that you see using, you see during the tarmacking of roads is the bitumen. It's the tar obtained from the bitumen. So it's important to know those different fractions and how they are used. Okay, so since we had already gone over that, so I've mentioned that gas oil, or what we call fuel oil, is used to manufacture petrol. Remember, petrol is widely used even here in Uganda. You notice that some of the vehicles use petrol, some of the engines use petrol. So petrol is on a high demand. And the fractional distillation method is not sufficient enough to give us the petrol required to be used in the whole world or by different nations. So that means we need to have another source where we can obtain petrol. So in this case, gas oil comes in as a better solution. But remember, during the fractional distillation process, petrol came in as a second fraction. But when you look at gas oil, it's among the last fractions to be collected off. That means it's heavier. So how are we going to obtain petrol from that heavier fraction? And that is where cracking in comes in. So by just basic definition, what do you understand by the word cracking?
Frida, peace.
Yeah. On my side, I think that cracking is the process by which complex molecules are broken down into simpler ones.
Okay, That is good. Do you have any other suggestions?
And Nora Rosena.
Cracking is the breaking down of hydrocarbons into smaller useful pieces. Sorry, not pieces.
Okay, thank you. Okay, so like I've explained, when we come to oil and petrol, cracking is a necessary process that we are going to use. So when we are looking at cracking is the breaking down of complex hydrocarbons into simpler hydrocarbons. So in this context, the oil gas is the complex hydrocarbon, but then it's being broken down into simpler hydrocarbons of petrol. So another way we could obtain petrol to the required amount, because to the required amount, you're going to realize that we'll need to use cracking, because remember the fractional distillation gives us about 20% of petrol. So 20% is really too small. So we need to increase this percentage by cracking the gas oil to give us the petrol. I hope that is clear. So fractional distillation of crude oil yields only 20% of petrol, yet there is an increase on its demand, hence cracking of gas oil. Cracking is the process of breaking down long-chain hydrocarbons into shorter chain molecules. Then, of course, the large molecules of oils can be broken down into smaller molecules of petrol and gases by cracking. So the large molecules of oil can be broken down into smaller molecules of petrol and gas by cracking. So basically, that's it about crude oil. And then the different involvements in crude oil. So you need to know how is crude oil obtained, how is it purified, that is the fractional distillation method, and then what are the different uses of those fractions obtained, and then you also need to know about how can we obtain more petrol beyond the 20% that is given to us during fractional distillation. So today we are going to stop there, but in our next lesson, I want you to research about natural gas. What is natural gas? How is it obtained? And then what are its uses? So those are things that you should come knowing in the next lesson. So since I didn't give us a break, the break will be for now. So for those 15 minutes, you can decide to breathe for 5 minutes, then you use the remaining 10 for finding out about natural gas. So if we have any questions, I could take them now.
Zara, please unmute.
Teacher, could you please help me and send the first, when the lesson is done, and send the first lesson slide in the group, because unfortunately I was not able to attend it, so I still want to write those notes.
Okay, but I think I'll just share all the slides we've used for learning today so that even the ones that kept joining in can keep a track of
No,
what we learned.
I mean the first lesson, like not this slide, like the first lesson you had. This is your third lesson, right?
The slides are already on the group. So if you're on the group, they are there.
But I'm new now, so I don't have the old slides.
Oh, so are you on the group?
Yes, I am.
Okay, we'll see how to resend them.
Thank you, madam.
Right.
Then Happy, please unmute.
Madam, my question is just, when is the next lesson? Because I don't have a clear timetable about the lesson.
The chemistry lessons are always on Friday.
Okay, thank you.
Okay. All right, can we get someone to pray for us? Thank you for being a good class. And thank you for your activeness and participation during the lesson.
For this lesson that we have had today, we thank you for the teacher. Thank you for your lovely come and teach us, Lord. Lord, as we end this lesson, we pray that you can bless each and every person who has attended, and even those who aren't able to attend, Lord. Help them to attend next time and understand. Thank you, Lord, for blessing us with the spirit of understanding.
Amen. I don't know if the person is still praying.
Amen.
Okay, thank you so much, Semakula, for helping me coordinate, and thank you everyone for